Hi everyone, the paper I present in this video is RFD-IDS, Radio Frequency Based Distributed Intrusion Detection System for the power grid. My presentation will first introduce the paper and its key ideas, and then discuss the strong and weak points of this paper. For the convenience of the speech and to highlight the key points, I have adjusted the order of the article and skipped some parts, such as the background knowledge of the power system and electromagnetic fields. Now, let's start to look at this paper. As we know, the power grid is a highly complex control system and is one of the most impressive engineering facets of the modern era. Modern facilities critically rely on the proper operations of the power delivery systems. However, in recent years, due to the expansion of the power system and the development of the smart grid, more and more communication links, computers, laptops, and remote access have been connected to the power system. This increase in the connectivity and the great complexity have led to a larger attack surface, making the cyber attacks a growing threat to the substations. In 2015, the world's first successful cyber attacks on substations happened on the Ukrainian power grid. The hackers shut down all circuit breakers of 30 substations, leading to a blackout more than 6 hours. In this attack, besides the malicious control on the circuit breaker, and the hackers also injected false operating data to the supervisory control and the data acquisition system, which is the SCADA system, and thus reported a normal operation condition to the control center. Another key aspect of the incident is that the distributed denial of service attack on the call centers prevents the customer's complaints from being received by the power company. As a result, the company was unaware of the attack until it is too late. After this attack, the number of power outages due to the cyber attack has increased dramatically. So there is an increasing demand for the intrusion detection system that can more reliably and robustly detect the cyber attacks on the grid. The existing IDSs focus on the securing power substations through monitoring the network traffic of the SCADA system. Accordingly, if the hacker can compromise the SCADA system entirely, the IDS will not be able to detect the malicious activities in the substation. Motivated by this fact, the aim of this paper is to propose an air-gap distributed IDS, which monitors the substation activities by radio frequency measurements to verify the correctness of the SCADA network traffic. With this approach, the SCADA system is assumed to be an untrusted entity. Power system cybersecurity has been traditionally handled using network security and internet technology practice. One common feature of these works is they require some level of trust on the SCADA system. Therefore, most of them are vulnerable since the SCADA system can be compromised. Another attack detection method emerging in recent years is the physics-based IDS. The idea is that the cyber process can be monitored directly through the physical channels since they emit physical emanations of different modalities. Since the interconnection between the physical world and the cyber world is not separable, any malicious operations can be determined based on its physical emanations. Previous efforts have used the physical channels to estimate the running state of physical devices. Electromagnetic emissions, acoustic emission, power fluctuations, and the thermal output variations are mainly used by this physics-based IDS. The RFD IDS also belongs to this type of IDS, but different from these works. In the proposed method, the low-frequency magnetic field is leveraged to estimate the operations in substations, and a global lightning authentication scheme is used. Before diving into the RFD IDS, the threat model should be discussed. The main assumptions of the threat models are: First, the SCADA system is totally compromised by the attackers and hence is untrusted. Then, it assumes that the knowledgeable attacker will be fully aware of the substation configuration, its control mechanism, and even the algorithm of RFD IDS. Last but not least, the GPS is a secure and a trusted entity. In this paper, the possible attackers are classified into 4 main groups. Attacker level 1. The attacker has the background in the SCADA security, but he has no knowledge on the electromagnetic analysis. Attacker level 2. This attacker has the background in both the SCADA security and the electromagnetic analysis. Attacker level 3. The attacker has the background in both the SCADA security and the electromagnetic analysis, as well as complete knowledge and access to the Lightning database. Attacker level 4. The attacker has the background in both SCADA security and electromagnetic analysis, as well as complete knowledge and access to the Lightning database and the geographical information about the power grid. Now, let's look at the RFD IDS and how it could deal with each level of attacker. The basic idea of radio frequency-based IDS is that any AC circuit in a substation invariably emits a magnetic field, which the receiver used by the paper can very easily detect. There are 4 types of information the RF magnetic field receiver will capture. They are the harmonic content of magnetic field, the fundamental frequency of magnetic field, which is usually 60 Hz, the impulsive emission in the magnetic field, and the lightning spherics in the magnetic field. The first 3 quantities will be used to reconstruct the flowing current and switching operations in substations. Then, they will be compared to the SCADA network traffic. If any difference found between the SCADA measurements and the RFD IDS measurements, for example, the current amplitude measured by the SCADA system and the current reconstructed by the RFD IDS is different, it means the false data has been injected into the SCADA system. The global lightning information will be extracted from the last quantity, the measured lightning spherics, and then be compared with the global lightning database or second lightning database to check the integrity of the data. Because the quasi-random sequence of the global lightning can serve as a watermark of the magnetic field signal, they can be used to authenticate the collected data. So meaning that the low frequency magnetic field data cannot be spoofed or played back by an attacker. All of this is called global lightning authentication, and it provides an air-gapped and redundant mechanism to the power system, monitoring, and the diagnostics. As the proposed method is non-invasive, it can be easily applied to existing substations. Let's discuss more about the global lightning authentication scheme, which is one of the key ideas of this paper. Typical LF data contains not only the power line harmonic radiations and impulses, but also the spherics from global lightning strokes. Magnetic field signature in a single second and 12 milliseconds at 3 sites in Georgia are shown here. You could see a lot of lightning signals during this time, and we will call the data in this period of time the moving time window. With the knowledge of lightning times and the locations, one could easily check the impulse arrival times are consistent with the global lightning database. Specifically, a moving time window of data was first extracted. Then, it was validated by simply accounting for the worldwide propagation delays close to the speed of light, calculating the expected arrival times of spherics, and then verifying that the pulses did appear. If hackers has perfect knowledge about the global lightning activities, as the shape of the spheric evolves with distance and as a function of time of the day, season, and other factors, synthesizing accurate LF data will require computational intense physical models of the propagation between the Earth and the ionosphere that cannot be run anywhere near real time. As such, the quasi-random distribution of the global lightning makes for a one-way function that allows easy authentication but is practically impossible to synthesize. In this paper, the National Lightning Database (NLDN) is used as the second input. Besides the NLDN, the third input, the secondary lightning database formed by nearby receivers, is also critical to detect intrusions. Let me explain the second database in more details. The time and the location of lightning strokes can be determined by three receivers forming a triangle. So at least three receivers in nearby substations will be chosen to form a receiver network for the protected substation. This receiver network will establish its own lightning database and send it to the protected substation as a third input. Any inconsistency between the arrival time of the spherics in these three inputs will likely be a sign of intrusion. After understanding the global lightning authentication, we are able to understand how RFD-IDS works against the different level of attackers. For level 1 attackers, the SCADA system is compromised, so the hackers could maliciously control the circuit breaker and report a normal condition to spoof the control center. However, since hackers are not aware of the global lightning authentication, the data injected to the SCADA system does not have lightning information. Hence, it could be detected by the RFD-IDS. For level 2 attacker, the SCADA system and the LF receiver in the protected substation are both compromised. Since real-time calculation is less possible, the lightning signals added to the magnetic field data by the hackers are probably replayed data. Therefore, the arrival time of the lightning signals are different from the global lightning database. Therefore, the RFD-IDS can still see this difference. For level 3 attacker, even the global lightning database is hacked. However, the second database established by other receivers in nearby substations will still be different. Similarly, for level 4 attackers, even though a portion of receivers are hacked, at least one receiver report the correct magnetic field data. The secondary database will still be different from the primary lightning database. Remember, the inconsistency will likely be a sign of an intrusion. To validate the proposed method is able to detect the malicious operations. This paper presents some experimental and numerical results under different attack scenarios. The first attack scenario is the circuit breaker malicious switching. Let's first discuss the malicious opening of a circuit breaker. The biggest change due to the opening is the change of current magnitude. Before the switching, the rated current is flowing through the substation, while after the switching, the current level should largely decrease due to the cutoff of the source. Therefore, we should observe a significant drop in the H-field data, and especially the fundamental frequency. The figure shows the H-field waveform on the top and the 60 Hz component on the bottom, before and after an opening event. The impulsive indicate that the circuit breaker is open. You could see 3 peaks in the top figure, which probably caused by 3 phases of the current. In the bottom figure, the decrease of 60 Hz component after switching can be clearly observed, and this is in line with what we expected. Since the switching is legitimate, we can observe the trip command is sent to the circuit breaker at 11:09, utilizing operate function code in the DNP3 protocol. Similarly, the closing of the circuit breaker could lead to an increase in the fundamental frequency of the H field. However, if this switching operation is malicious, no matter whether we can see the trip command in the SCADA traffics or not, this intrusion can be always detected by the RFD-IDS. The second attack scenario is transformer type changing. Let's escape the principle of the transformer and the transformer tap changer. In simple terms, the transformer tap changing can change the ratio of the transformer, and therefore change the output voltage and output current, and cause overheat and energy waste. Due to the complexity and the consequences of conducting such experiments in a real substation, numerical simulations are used. The circuit in the top figure is used to simulate the current change after the transformer tap changing, and the simulation results are shown in the bottom figure. In this figure, the tap change happens at 10 seconds, so the real current has a big shift due to the attack. Since hacker has injected normal data to the control center, the spoofed data remains unchanged. However, such a shift in the current can be measured by the LF receiver, and this malicious operation can also be detected. The last attack scenario is false data injection to substation RTUs. This is the most common attack to substations. Instead of switching circuit breaker or changing the tapes of transformers, hackers can cause a serious consequence by just changing the current amplitude or phase angle. To ensure this change can be detected by the RFD-IDS, 3 phases of actual current and the RFD-IDS reconstructed current before and after the opening event are compared. The errors are shown in the table 1. Even in the most severe cases, the error is only around 10%. So if the threshold is set to 12%, any manipulations on the SCADA measurements can be detected. For those attacks which change the current level slightly, like less than 12%, the influence is very small. In the last chapter before the conclusion, the paper shows the robustness and the resilience of RFD-IDS in 2 stages. First stage is magnetic field validation state. The RFD-IDS should detect the lightning interference in a certain accuracy to satisfy the requirements of global lightning authentication. The second stage is measurement and command validation state. The RFD-IDS can reliably capture the fundamental and harmonic components of the H field, so that the current value, including the magnitude and the phase angle, and switching operations can be reconstructed correctly. In the lightning authentication stage, the paper considered 2 issues. The first issue is the length of moving time window. The lightning authentication scheme checks the magnetic field signal's integrity in a moving time window, as mentioned before. So the length of the window is a very important parameter. If the length of the time window is too short, there is a possibility that no lightning interference is detected in some time windows, and thus the authentication scheme becomes vulnerable and too conservative. On the other hand, if the length of the data window is too long, the proposed IDS will experience too much delay in identifying the malicious activities in the substations. Accordingly, a reasonable trade-off should be made between the number of interferences in the current time window and the length of that. To determine the proper time, a series of experiments is conducted, and as shown in the figure, 2 consecutive interferences can be detected both by the LF receiver and the lightning database in a time window with the length of 2 seconds, and the probability can reach 99.99%. Therefore, by considering a moving data window with the length of greater than 2 seconds, if the attackers feed the algorithm with a spoofed signal without any interference, the chance that there is actually no lightning in this moving window is less than 0.01%. That is to say, the hacker will succeed with the probability of 10 minus 4. Another issue in the lightning authentication stage is the level of consistency between the three inputs to the authentication scheme. As shown in the left figure, the global lightning database can pick up a major portion of the lightning cipherics in each time window, while the RFD-IDS receivers are able to pick up only a subset of those cipherics. With a similar reasoning, the probability that a cipheric shows up in the secondary database formed by the network of the receiver in nearby substations is more than that of a single receiver and less than that of the lightning database. So, there is a probability that the cipheric is not detected by the awesome receiver, and its corresponding data does exist in the primary and the secondary lightning database. To solve this problem, the paper defined a threshold for the number of inconsistency in each time window. As shown in the right figure, with the time window length of 4 seconds and the threshold of 3, the paper achieved a 99.99% true positive rate. In the second stage, the paper evaluates the performance of the current reconstruction algorithm. The current reconstruction algorithm will reconstruct the current based on the measured magnetic field. There is the possibility that in a real substation, the current will not only be the sine waveform, but also be the complex waveform in some abnormal cases. The algorithm should be able to reconstruct the current even in these cases. Two current signals which separately have more harmonic and fundamental frequency components are estimated by the algorithm. The left figure shows the estimated current in blue and red current in orange, and the right figure shows the actual current in blue and estimated current in orange. They are separately evaluating the performance of the estimation algorithm on the harmonic and the fundamental frequency. To simulate the worst case, 10% or 20 dB SNR Gaussian noise is superimposed onto the reference input signal. According to the figure, the adopted algorithm is robust against the noise and abnormal operation conditions, even in the worst case, which implies the practical merits of the proposed approach in the real-world application. Finally, I want to talk about my idea about this article. The paper proposed an intrusion detection system based on the low-frequency magnetic field. Choosing the low-frequency magnetic field as the physical emanation is actually an advantage, not only because the use of the magnetic field enables the non-invasive measurements and monitoring, but also because the low-frequency magnetic field is hard to be shielded. It can penetrate the SiC-grounded metal enclosure like the Datang SF6 circuit breaker, and therefore the LF magnetic field can carry more information compared with other physical channels. Another strong point is the global lightning authentication scheme. As far as I'm concerned, this is the core finding of this paper. It is a very innovative way to detect the intrusion. The best part of the RFD-IDS is that it can check the integrity of itself, which means do the self-validation based on the global lightning authentication scheme. This is the method which is full of the potentials. Also, I see some weak points of this method. The assumption does not say the hacker do not have the LF receiver. So what if hackers have one or more receivers and can measure the magnetic field around the target substations? It does need some knowledge about the electromagnetic fields, but since the paper of the receiver used by RFD-IDS is open online, it is still possible that the hacker can create or recreate a receiver to measure the low-frequency magnetic field. Indeed, synthesizing the lightning data is less possible, but the hacker can just measure and extract the lightning signal and superimpose into the false data, which means the injected data will have the correct lightning interference. In this case, how does the RFD IDS find the intrusion? Second, the paper only talks about the low limit of the length of the moving window, which is 2 seconds. So is the 2 seconds short enough for all the cases, all different power systems? What is the upper limit of this length if I want to achieve a even higher accuracy? Those are the questions the paper does not answer. Overall, the IDS proposed by this paper is very innovative and full of potential. It is a very good paper and ideas, and it is worth to read. That's all. Thank you.